Assalamualaikum warahmatullahi wabarakatuh, and hi to everyone. Now we continue our lesson 5 on chapter 3, electric current and direct current circuits. So in this lesson we have 4 main subtopics that we need to cover: 3.6, 3.7, 3.8 and 3.9. Okay, let's review our learning outcomes for these 4 subtopics, which is 3.6 until 3.9. The first one is 3.6, Kirchhoff rules. So you need to know how to state and describe the Kirchhoff rules and how to use the Kirchhoff rules. Okay, next subtopic is 3.7, electrical energy and power. So you need to know how to use the equation of power. Okay, P equal to IV, or you can use P equals to I square R, or the other one you can use P equals to V square over R. Okay, and second in outcomes, you need to know how to use the equation of electrical energy, okay, which is work or energy equals to VIT. Okay. Subtopic 3.8, the potential divider. Okay, the first in outcome is you need to know how to explain the principle of a potential divider. And second is how to use the equation of potential divider. V equals to R1 over with R1 plus with R2 and multiply with V. Okay, and next subtopic is 3.9, potentiometer. So the first outcome is you need to know how to explain the principle of potentiometer and their applications. And second is use related equations for potentiometer, which is EMF 1 over with EMF 2 equals to L1 over L2. Okay, how to use all the equations, you can apply it in tutorial mode. Okay, let's discuss subtopic 3.6, Kirchhoff's rules and learning outcome in lecture mode for Kirchhoff rules is state and describe Kirchhoff's rules. Okay guys, for your information, we have 2 types of Kirchhoff's rules. Okay, number 1 is, okay, this is number 1. Okay, number 1 we call as Kirchhoff's first rule, and this is about the concept of current at any junction. Okay, for the first Kirchhoff rule, okay, for the first Kirchhoff's rule, we have 2 statements. The first one is the algebraic sum of the currents at any junction is 0. Okay, you can see it in mathematical equation. The total current is equals to 0 at any junction. Okay, or our second statement for first Kirchhoff's rule is total current entering a junction is equal to the total current leaving the junction. Okay, and the mathematical equation is total I in equals to total I out. Okay, and it is about at any junction, because as I mentioned earlier, Kirchhoff's first rule, it is about the current at any junction. Okay, look at to the explanation. Okay, first Kirchhoff's rule is a statement of the conservation of charges. Okay, because it is about your current flow. Okay, once you have the current flow, it is about the charge in circuit. Alright, so look at for the explanation. Okay, whatever current enters a given junction in a circuit must leave that junction, since charge cannot be created or destroyed at any junction. Okay, so that's why current in can be equals to current out. Okay, and the second explanation, charge cannot escape from the wire but has to flow around the circuit. Okay? Okay, now I will explain about the Kirchhoff's first rules, because you have two methods, right? Okay, total current equal to 0 at any junction, and second is total current in equals to the total current out. Okay, you can use either one lah. Okay, let's say let's say you have this type of junction. Okay, I just take a part of the circuit. Okay, in your circuit you're gonna have batteries, switches, or any resistors. Okay, right now let's say you have current 1 towards the junction. So junction, I make it a circle to make it clear. Okay, so now your current 1, it is towards the junction, towards the circle. So I write this one as in. Okay, so this is in. Okay, and as we know, current would be split into other currents. Okay, because your current cannot be created or destroyed. Okay, once your current reach any junction, current will be separated or split in other currents. So I make it as I2 and also I3. And now we can see that I2 and I3 both are out the circle. Okay, out the junction lah. So it is out the junction. Okay, now based on the second statement of Kirchhoff's first rule, which is total current in is equals to total current out. Okay, so we can see that in, okay, for the current in, it is our I1. And the current out, you have two current out. Okay, two currents, which is I2 and I3. So I2 plus with I3 lah. Okay. Or you can remark I1. Okay, I1 is towards the junction. Okay, it is towards the junction. Okay, while I2 and I3, it is away the junction. Okay, so that's your second statement of first Kirchhoff rules. Or actually, it is similar with total I equals to 0. Because if you sum up all the current, I1 minus with I2 minus with I3, you will get 0. So you have two methods, either total I in equal to total I out, or you can use total I equal to 0. But I suggest you use this one. Okay, total current in equals to total current out, because it is easier for us to solve in mathematical way. Okay, our second rule, Kirchhoff second rules. Okay, and this is related with the loop or voltage rule. Now look at to the statement of Kirchhoff's second rule. The algebraic sum of the voltages across all of the elements in any closed loop is 0. In mathematical equation, the summation of EMF plus with the summation of product current and the resistance is equals to 0. And the total or summation EMF, this is about our sources. Okay, our source, usually this is the battery. Okay, you can have more than one battery. And this one, the summation of product current and the resistance, this is known as the voltage drop. Okay, voltage drop across resistor. Okay, because of the opposition of current by the resistance. Okay, now we will discuss about the sign convention in Kirchhoff's second rule before we apply the rule to solve any equation. Alright. We have the direction of traverse. Okay, all of our diagram, direction of traverse is from A to B. Everything from A to B. Okay, now look at to the first diagram. If the direction of current is in the same direction of traverse, okay, traverse you from A to B, okay, from A to B. So this is in the same direction. So in the same direction, you will have the negative potential difference. Okay, negative potential difference, which is negative IR. Okay, potential difference, it should be final minus with initial, VB minus with VA. Okay, simple. If you have the same direction between traverse and current, the potential difference is negative. Now, the second diagram, if the direction of current is opposite with the direction of traverse, because traverse is from A to B. This is in opposite direction. If opposite direction, the potential difference for this resistor, it becomes as a positive. Okay, positive. And next, for the battery itself. Okay, from the battery, if your direction of traverse, okay, direction of traverse in the same direction of current flow, because current flow from positive to the negative, so in this direction lah, in this direction, okay, in the same direction. So if it is in the same direction, the potential difference for this EMF is positive EMF. Okay, same goes with the last diagram. If direction of traverse is to the right, but for the EMF, okay, EMF is opposite with the traverse, okay, because current flow from the battery from the positive to the negative. Okay, so it is like this lah. Okay, so this is in opposite direction, in opposite direction. Therefore, the potential difference for this EMF is negative sign. Okay, so for these four signs convention, we will use it to solve the equation. Okay, our second statement, okay, because Kirchhoff's rules, okay, for first Kirchhoff rule and second Kirchhoff rule, it has two statements. Okay, so for the second statement, we can use this one. It is stated as the algebraic sum of EMFs is equal to the algebraic sum of the products of current and resistance in any closed loop. Okay, you can use either one for the first or second statement. In mathematical equation, okay, we have the left side and also the right side. So this is our equation. Okay, the summation of EMF equals to the summation of product current and resistance. And it should be in a closed loop. The condition is make sure your circuit is in a closed loop. Okay, now look at to the sign convention. Okay, it is similar with before. If the direction of traverse, okay, direction of traverse is same direction. Okay, this is the direction of traverse. Okay, the blue color represent traverse. Okay, the blue color is traverse. Right, and this is in the same direction with EMF. Okay, EMF, because this is positive and this is the negative. And we can see that this is in the same direction. If the same direction, your EMF would be positive. Okay, similar with the previous one lah. Okay, and if I use other colors lah. Okay, orange color. Okay, if direction of traverse, okay, direction of traverse is opposite with EMF, okay, because EMF U is like this to the left, okay, to the left, and direction of traverse, okay, blue color is traverse, so traverse is from left to the right, so this is in opposite direction. Once opposite direction, your EMF become negative. Okay, simple. Same direction, positive. Opposite direction, negative. Okay, similar with the resistor. Okay, for the resistor. For the resistor, the red color represent direction of current. So blue is traverse, right? Okay, the blue color, this one is your direction of traverse. Okay, direction of traverse, which is to the left, from right to left. And if the direction of current is opposite with traverse, okay, the product current and resistance become as negative. Okay, and if in the same direction, okay, direction of current in the same direction with traverse, okay, the product of IR become as a positive. Okay, I repeat once again. Same direction, positive. Opposite direction, negative. Okay, this is the method how to solve equation after this. Okay, right. Blue color direction of traverse or loop. Okay, and the red color represent direction of current. Alright, and this is a bit explanation. Okay, just a simple explanation about our Kirchhoff second law. Okay, our Kirchhoff second law. Okay, Kirchhoff second law is a consequence of the law of conservation of energy. Okay, energy before equal to energy after. That's why left equal to right. Okay, now if a charge moves around, okay, if a charge move around, okay, if a charge move around a loop, okay, a closed loop, okay, closed loop in a circuit, it must gain as much as energy it loses. Okay, what it receive, lose will be equal each other. Okay, and next, hence the gain in electrical energy by the charge equal, okay, equal to the corresponding losses in energy through the resistance. That's why, okay, the total EMF equals to the total product current and resistance. It is balanced to each other. Okay, now let's discuss example 3.13, and we need to find the current in each resistor in the circuit shown below. Okay, this is our diagram given to us. Okay, so we can see that you have two loops right here, and you have three EMFs or battery and also three resistors. Okay, simple. If you refer to this diagram, it looks like resistor in parallel, right? But it is not. Okay, so to solve this problem, to find the current, okay, to find the current, you need to use the Kirchhoff rules. Okay, why we need to the Kirchhoff rules? Because you have three different EMF in different wires. Okay, you have EMF 1, EMF 2 and EMF 3. Okay, simple. If you have more than one battery, automatically use Kirchhoff rules. Okay, use Kirchhoff rules to find the unknown value. Okay, if you have one battery, so this Ohm's law lah. Okay, but now different batteries in different wires, we use the Kirchhoff rules. Okay, this is our simple steps how to solve by using the Kirchhoff rules. Okay, the first one is you need to draw the current. Okay, draw the current, and this is a battery. What is a battery depends on us, or ikut suka hati. Okay, and second step is draw the loop, also a battery. And step number 3, apply the Kirchhoff's law. Okay, now we discuss one by one. Okay, first of all, you need to draw your current. Okay, draw your current, and this is a battery. Okay, and if you refer to the diagram, actually you have three different wires. Okay, you have three different wires. Start from here. Okay, start from here to here. Okay, this is one wire. Okay, start from here to here. This is second wire. Okay, first wire, second wire. And start from here to here. This is our third wire. Okay, so we have three different wires. So what should we do now? I clear up these things. Okay, you need to draw direction of current. Okay, depends on us. Okay, let's say I draw for the first wire direction of current 1 in clockwise. So this is current 1. Along this wire it should be current 1. Okay, you can't combine with other current. Okay, this is all current 1. Okay, next for wire 2 in the middle. Wire 2, let's say this is the direction of current 2. Okay, I label this is as a current 2. Next, our third wire at the right side, I choose this is as I3. Okay, so we know that to draw the current and to apply it, okay, it is occur in a at any junction. Okay, doesn't matter, we will discuss together after this. Okay, now second step is draw loop. Okay, draw loop also a battery. Okay, also a battery. And to draw the loop, you have two directions, either clockwise or anti-clockwise. Okay, it's up to you. Okay, it's up to you. As long as you follow the rules, you can get the correct answer. Okay, next, we draw it. Okay, so depend on me. Okay, so for the left loop, I make it as loop 1. Okay, because right now you have two loops, two closed loop. And loop 1, I want to draw it in clockwise direction. Okay, and next at the right loop, okay, the right side, I want to draw the direction in anti-clockwise. So this is as our loop 2. That's our reference. Okay, next. Okay, next is apply the Kirchhoff law. Okay, apply the Kirchhoff's law. And we have two laws. Okay, the first one is total current in equals to the total current out at any junction. Okay, at any junction. Okay, so if you refer to our circuit, this is our junction, Okay, this one as A and this one as B. So you can choose either junction. Okay, the product is the same. Just follow which one is inwards or towards junction and which one is away the junction. Okay, and second law. Okay, second law is the total EMF equals to the total product of current and resistance in closed loop. Okay, in closed loop. So we can see that your loop are closed. Okay, so you can apply it. Alright, now let's do it the mathematical equation. Okay, let's discuss this equation, how to solve the current. Okay, we need to draw the direction of current, I1, that occur on wire 1. Okay, I need to follow my previous diagram. And wire 2 is my I2 and wire 3 as my I3. You have 3 different wires, means you have 3 different current. Okay, alright, and we have 2 junctions, junction A and junction B. Okay, so you can choose either one, A or B. Alright, to solve the first Kirchhoff rules, which is the total current in equals to the total current out, just refer to the direction of current that reach the junction. Okay, so I choose A first. Okay, junction A. And at the junction A, I in represented by I1. Okay, I1. And I out represented by I2 and also I3. Okay, because it is away the junction A. So this is I2 plus with I3. Okay, and I make it this one as equation number 1. Or guys, you can use our junction B. Okay, for the junction B, we can see that I2 and I3 are out, are in the junction. Okay, so I2 plus with I3 for our I in, and away the junction it is by I1. So ini I1 lah. Okay, it is the same. Okay, if you refer to junction A and junction B, I2 plus with I3 equals to I1. That's why I mentioned it. You can choose either junction. Okay, then you can solve for second Kirchhoff rule. Total EMF equals to the total product current and resistance. But before that, don't forget to draw direction of the loop. Okay, at the left side, loop 1, I had decided this is in clockwise direction. Make sure in the same direction, okay? Okay, clockwise. Okay, and at the right side, the right loop, our second loop, I had decided this is in counterclockwise. Okay, counterclockwise. Okay, alright. Now, for loop 1, okay, for loop 1, we have two EMF actually. Okay, you have two EMF, EMF1, okay, EMF1, and also EMF2. Okay, if you choose start from A and must be in a closed loop, the end also at point A. Alright, so since EMF1 in the same direction with loop, same direction, ini negative and this one is positive. Okay, so it is in the same direction, so same direction, positive EMF1 lah. Okay, positive EMF1. Then for EMF2, negative terminal, positive terminal. Okay, and direction of loop also in the same direction with EMF. So this is a positive plus with EMF2. This is method, method. If you follow all the methods correctly, you can get the correct answer. Okay. Okay, settle for EMF. Now for the product of current and resistance. For loop 1, you just have one resistor, which is R1. Okay, R1, and the current that across R1 is I1. Okay, I1. Direction of I1 is in the same direction with the loop. So it is a positive lah. Okay, positive. Positive I1, R1. Then you can substitute all the values. Okay, so this is 10 plus with 5 equals to I1, R1 is 4.0. Okay, so simplify it. 15 equal to 4I1. Oh, okay, so you can find your I1. Okay, you can find your I1. The answer is 3.75 ampere. Okay, settle for I1. Next, refer to the second loop. Okay, for the second loop. So I separate it. This is for loop 2. Okay, for the loop 2. And we also have two. Okay, we have two EMF. Okay, we have two EMF. EMF2 and EMF3 for the loop 2. And now refer to the direction. Okay, direction of the loop and EMF is in the same direction. Okay, in the same direction, negative, positive. Okay, so then EMF2 is a positive sign. And your EMF3, okay, your EMF3, this is the direction of loop, negative, positive. So your EMF in the same direction with the loop. Okay, same direction, also positive. So positive EMF 3. Alright, settle for EMF. Now look at to the resistor. You have two resistors, R2 and R3. And you have the same of current that flows through R2 and R3 because it is occur in the same wire, so same current lah. Okay, but different resistor. Alright, now check the direction. Okay, direction current that across R2 are in opposite direction with the loop. So opposite direction means minus. So this is minus I3 R2. Okay, then for R3. Okay, for R3, this is the direction of current that across R3 and this is the loop. Okay, opposite direction. So opposite direction also negative. So negative I3 R3. Then you can substitute all the values. EMF 2 is 5. EMF 3 also 5 equals to negative I3 unknown. R2 is 4. Okay, minus this is I3 and R3 is also 4. Okay, and this is 10 equals to negative 8I3. Okay, then you can find your I3. And the answer is negative 1.25 ampere. Okay, don't be panicked why you got the negative sign. Okay, this negative sign represent opposite direction with our assumption. Okay, opposite direction with our assumption. That's it. Because I3 we choose it is in clockwise, right? But the real one is it is in anti-clockwise. Okay, settle for I3. Then you can find your I2. Okay, you just substitute into our first equation because this is okay, substitute. Okay, substitute into 1. Okay, so just rearrange. I2 equals to I1 minus with I3. And your I1 is 3.75 minus with negative 1.25. And the answer for I2 is 5 ampere. Okay, so the answer is 5 ampere. Settle. Okay, simple, right? Okay, good luck for Kirchhoff. Just follow the rules. Okay, and you'll be happy.